Now that we've put atoms together, let's start talking about what a mineral is. Now, the definition of a mineral has 5 parts. And in your typical intro to geology class, your instructor is going to say, learn this definition and know it by heart. It has to be naturally occurring and inorganic, solid, with a crystalline structure and a definite chemical composition to be considered a mineral. So naturally occurring. If you find some frozen ice outside that is water that has turned into a solid, it happened naturally. Snow, natural ice, is a mineral. But if we make ice cubes in our freezer, that's not considered a mineral. Same composition, but the process of how it formed can have a big difference on the definition. Now, your textbook says generally inorganic instead of just inorganic. And I think it's surprising to see that your textbook mentioned that shells of some organisms are made of chemical compositions that are the equivalent of minerals and that geologists would consider them minerals. Well, most geologists that I know would not consider a snail shell to be a mineral, although functionally they are equivalent in terms of what they're made of. Minerals have to be solids, so oil cannot be considered a mineral. There needs to be an orderly internal molecular structure. In other words, there has to be a crystal shape to it, a crystal form. So the atoms have to come together in particular ways in order to create that crystal. And there has to be a chemical composition that you can write down. Now, I say it's a formula that you write down, but there's going to be a little bit of latitude in there, because most crystals are going to have some atoms on occasion being replaced by other atoms of the same charge and the same size, roughly. So there is a little latitude, but keep in mind a mineral has to meet all 5 of these criteria. Now, when you start looking at minerals, the first thing most geologists want to do is identify them. In this course, we do not have a lab component, and so you will not be identifying minerals, but I do want you to know the basic properties that allow people to put a name on a particular mineral. Most of the properties are going to be easy to observe or involve very simple tests. For instance, here's a close-up of some really bizarre minerals, but if you look at them, you can see that there are distinct colors. The appearance looks a little bit glassy. There don't seem to be any flat surfaces. And so all these are features that we can use to start identifying minerals. Now, be sure you've read the textbook before you continue watching. Here is an image of a garnet, and you can see this image within your textbook. What characters of this garnet might be useful to identify it? Same question here. This is a chunk of pyrite. What characters can you see in this photo that might be useful in identifying this mineral? Now, your textbook went through a lot of different properties, and there are a lot of properties that geologists use to identify minerals. However, there's a couple basic ones. And most likely, anyone who sees a mineral, a rock, or almost anything, one of the first things you think about is, what color is it? Well, in the case of minerals, color tends to be one of the most worthless properties that you can use to identify something. Now, there are some exceptions. If you see something that's green, that tends to be indicative of a mineral that has copper or iron in it, and that can help you identify it. But in the case of the photo on the lower left, we have white and purple and dark orange and charcoal, almost black color. All those minerals are the same thing. They're all just quartz. Quartz can come in any color whatsoever, and there's a lot of minerals that come in a wide variety of colors. So most geologists are going to look at color for just a couple minerals, and even then only after looking at some other properties. Now, a better property, a better easy to observe property than color is the streak. The streak is the color of the mineral when it's in powdered form. In this upper right photo, there's a shiny metallic lump called specular hematite. Now, hematite can occur in a blood red form. It can be shiny, it can be dull. So it can have different colors. But if you take it and you grind it up, and the easy way to grind up a mineral is to rub it back and forth on an unglazed piece of porcelain. And that's the white square that you see within that photo. Now that shiny piece of shiny black lump has a streak that's a dark reddish brown. Regardless of the color of that mineral hematite, that streak will always be a dark reddish brown. So that's going to be a more diagnostic character. If we go back to the chunks of quartz on the lower left, all four of those are going to give you the same color streak. In all four cases, the streak is going to be a fine white powder. It doesn't matter if the macroscopic, the hand-sized version, is purple or dark orange. The streak will be a consistent white color. Another easy to observe character just by looking at a mineral sample is the luster. So how does it look in reflected light? And your book talks about a lot of different kinds of luster, including glassy and pearly and satiny. Well, geologists typically only use two major categories of luster. Does it look like a shiny piece of metal or not? So is it metallic or is it non-metallic? Now, crystals are going to have unique shape for two different reasons. One is how the crystal grows out of a solution. And that solution can be a magma, it can be a water solution. So that pattern of how the crystal grows will be the crystal habit. However, geologists tend to break things. And that's because the crystal habit is not as useful of a character as how a mineral breaks. A mineral can break in a couple different ways. The two primary ways are along cleavage planes, which is planes of weakness at the atomic level, or some kind of fracture. Now, these cleavage planes are going to be perfectly flat planes. You can physically put your hands on them. And in fact, if we were doing a geology lab, I would ask you to put your hands where the cleavage planes are. There are a couple different possibilities. And so you have most of the possibilities listed on the screen in front of you. You can have sheets of mica that have one cleavage plane, and they break off like pieces of paper. You can have two planes of cleavage that either meet at right angles or that do not meet at right angles. And the difference between these is also going to be based on the atomic arrangement of silica oxygen tetrahedra. And I'll get to that in just a couple of minutes. There can be 3 degrees of cleavage at right angles or not at right angles. There can be 4 directions of cleavage toward the very bottom, and those look like 8-sided dies. Those particular ones are pieces of fluorite, which is the Illinois state mineral. Now, not shown on here is the last option for the number of cleavage directions, and that's 6. Now that one is much more difficult to see, so there's not a good picture that I found for that. Here are some close-ups of a couple different minerals. So going from left to right, write down how many planes of cleavage each of these have. And then if they have 2 or 3 planes of cleavage, tell me, are these planes intersecting at right angles or not at right angles? Now, if a mineral does not break along flat planes, in other words, it does not have cleavage, it will have some kind of fracture. The 2 most common types of fracture are conchoidal fracture and irregular fracture. Conchoidal fracture is one that will be common because we see it in quartz, which is one of the most common minerals on the Earth's surface. So conchoidal fracture, like the picture here, is along smooth, curved surfaces, like broken glass. An irregular fracture will have a rough surface and no discernible pattern. The density of a mineral can tell you something about what's in it, as well as what the atomic arrangement is. Within geology, we refer to density more in a more specific way in terms of specific gravity. So this is a ratio. It's the weight of a particular mineral or any other substance compared to the weight of an equal volume of water. So when you have a specific gravity number, there are no units beside it. And at the bottom here I have a few examples of the specific gravity of a few items. Styrofoam has a specific gravity less than 1, which means it's less dense than water. Styrofoam floats. Coal and limestone are common rocks that you can find in central Illinois. And you can see some of the highest specific gravities in metals. Gold has one of the highest specific gravities of any naturally occurring object. Hardness is commonly measured on the Mohs scale. Now this is not referring to how hard is it when you knock on it or when you throw it against the wall. It specifically refers to the resistance to scratching. The Mohs scale is very commonly used because it's simple. So it consists of 10 different minerals that are on this relative scale. And along this scale, we have common objects that we can place in here as well. So if we were doing a lab, I would ask you to have a copper penny, a nail, a knife blade, piece of glass. And so by taking that piece of glass and a mineral, rubbing the mineral across the glass, we can see, does that mineral scratch the glass? Which means it's greater than a 5.5 on the Mohs scale, or does it not scratch the glass, in which case it'd be below a 5.5. Now keep in mind this is just a relative scale. It's not meant to be a very accurate scale in determining absolute values of hardness. In other words, if you have a mineral that's a 4 on the Mohs scale, in this case fluorite, compare that to a 2 on the Mohs hardness scale, such as gypsum, the fluoride is not twice as hard. It's simply harder. Now there are many other properties, and I just want to run through a couple more. Most of these properties are specific for one or just a couple minerals, and therefore they're not as widely applicable. In the case of streak or in the case of hardness, every mineral is going to have some kind of value. But in the case of reaction to hydrochloric acid, that's only going to apply for a few. Calcite, an extremely common mineral around here because that's the mineral that makes up limestone, reacts very quickly to cold hydrochloric acid. The mineral magnetite will allow you to stick magnets to them, so it's magnetic. Some minerals like halite are going to have a distinct taste. Halite is simply table salt. So if you lick halite, it's like licking a pile of salt. Some minerals are going to have distinct smells like sphalerite. If you take sphalerite and grind it up, it smells like rotten eggs. And then if you have a clear piece of calcite, not only will it react with hydrochloric acid, but it has a property called double refraction. This is because at the atomic level, light enters it and is split into two different rays. So as light passes through a piece of calcite, it's split and you see a double image. Now when you start identifying minerals, don't get overwhelmed by the fact that there are more than 4,000 named minerals. Instead, if you learned 40, maybe 50 minerals, you would be able to identify most of the rocks that occur on this planet. So just learning a few properties can allow you to learn a few minerals. A few minerals can allow you to identify a lot of rocks. Now if you look at what are the elements within the crust? There's only 8 that make up the vast majority of the crust, more than 98%. So most minerals are simply made up of some combination of those 8 elements. When we look at the crust, we see these as the 8 most common elements within the crust. Specifically, we can focus on these top 2, oxygen and silicon. So because these are the 2 most common elements in the crust, they're the 2 most likely to get together and form minerals and to eventually form rocks. So silicon and oxygen together create a silicon-oxygen tetrahedron, and that's pictured on the right. You have a single silicon atom shown in blue in the center, surrounded by 4 oxygen atoms. Now, silicon and oxygen make up most of the crust, so it makes sense that most of the minerals are made up of silicon and oxygen, and those silicate minerals are making up most of the crust. Silicate minerals are put into groups based on how the silica tetrahedra are put together, or in the case of this first group at the top, the olivine group, not put together. So in the case of olivine, you have independent tetrahedra. They're not linked directly to each other. As a result, you cannot form planes of weakness, and minerals like olivine do not have cleavage. For the second and third, we start putting together these silica tetrahedra. When you put them together in single chains, you're going to create an arrangement that allows cleavage to form. The next more complex arrangement is 2 chains, single chains combined together. Now, in the case of both a single chain and double chain, the minerals are going to have 2 planes of cleavage. But whether they meet at right angles or not at right angles is determined by whether it's 1 chain or 2 chains. The next most complex arrangement is putting together the tetrahedra into sheets. In this case, you create minerals that have only 1 plane of cleavage. These are the micas, the ones that flake off like sheets of paper. The most complex is silica tetrahedra put together in a 3D network. In this case, you have a variety of different cleavage types. Mainly, it's going to be at 2 planes right at 90 degrees, or conchoidal fractures, such as in the case of quartz, listed here as not having any cleavage. It has conchoidal fracture instead of cleavage. The other major group of minerals are the non-silicates, the ones that might have some oxygen in them, but they never have a silicon-oxygen tetrahedron. The non-silicate minerals are named by their anion, that negatively charged ion, or they're just a single element by itself, like gold or copper or silver. Now, there's 2 non-silicate minerals that are going to be far more abundant than others, so I'll specify those here. Calcite, which I just mentioned, makes up the limestone that's all over central Illinois, and that has a chemical formula of Ca, or calcium, and then CO3, carbon, and then 3 oxygen. That carbon and 3 oxygen is a carbonate anion, and that means that calcite is part of that carbonate non-silicate mineral group. In the case of halite, or table salt, it's that last part, that chlorine atom, that makes it part of the halide group. Halides refer to the elements chlorine, fluorine, bromine. Now, whether it's a silicate or non-silicate mineral, we probably want to mine it for some reason. So if we want to mine something, we need to think about how long is that going to last. Essentially, anything that we're mining is a non-renewable resource. If it can be replenished over short time spans instead, it's a renewable resource. And I always was disappointed by that definition. Renewable resources can be replenished over a short time span. And I'm disappointed by that because we're talking about geology here. In the world of geology, millions of years to some people can be considered short time spans. So instead, let's kind of change that definition a little bit. A renewable resource can be replenished during your lifetime. Or it's something like solar power, which effectively never runs out. A non-renewable resource, on the other hand, takes millions of years to accumulate into any significant deposit. Now, your book uses the term mineral resources. And I want to introduce another term because it's useful when we start thinking about not just minerals, but also oil resources and oil reserves. Now, mineral resources is all deposits of some mineral that we know about and that we don't know about, that we can extract profitably, or that we might be able to extract profitably in the future. And that might refer to changes in the economy, or changes in technology, changes in demand. So it's all the known and the maybe in the future. Mineral reserves are a little bit more concrete. It refers only to the known deposits that at this point can be extracted profitably. So if you're running a business, you're probably more interested in the mineral reserves when you start to make immediate plans. If you're starting to make plans for the next 50 years and you're trying to make stockholders happy, then you start talking about mineral resources.